So today we consider such topic as normal approximation to the binomial distribution. This topic is really interesting because it can show how you can use binomial distribution and approximate it by using normal. You'll see that it is important to know sometimes like this. And we have learned before that the binomial distribution can be used to solve different problems. Like we have to find the probability of obtaining exactly 60 heads with 100 tosses of a fair coin. So it's easy to do by using this part. But to find the probability, like of obtaining 60 or more heads, we must find the probability of 60 heads, for 61 heads, for 62, etc., and then put them all together. So this is quite difficult because if you want to find just one thing like this, you can easily calculate. But imagine that you have to find the probability that you obtain 60 or more heads. So you need to sum up all of these things. It will be a disaster. And that's why we can use a kind of, I think, very interesting approach for normal approximation. It's not possible to do it quite quickly if you do it like summing up. Yeah. So, and in this situation, we can try to use this method using the normal distribution. I hope this is understandable because this is really interesting stuff. But in order to do this, we need to understand that binomial probability distribution can be approximated. Now let's have a look into those things below. Look here and just explore that. We have a situation here. What we have here, we basically have n equals 2, probability equals 0.5. So you have 2 times tossed a coin with probability 0.5. And then you have the distribution. You can see that the probability that you'd have 0 heads, let's say, so is 0.5. If you have 1 head, it's 0.25 for 0 heads, 0.5 for 1 head, and 0.25 for 2 heads. You can calculate it easily. But as soon as you make the number of trials larger, then you will see the following kind of thing. And you increase that, you will see kind of the following thing. What we have that when the number of coin tosses increases, the shape of the probability distribution becomes increasingly normal. It becomes increasingly normal. And you can see that it looks like a normal distribution. So we can just try to draw the curve here like this. You can see that. And the more you take, the better. But we need to figure out that. So if we have the same, so does the binomial probability distribution maintain its normal shape for large values of n when p varies? We have to speak about this using several types of modeling. You can find on the GeoGebra website this part, so it's also possible. I can show you a little bit like that, so it could be interesting as well. Because let's have a look into this part. So here we have it. And if we have it like that, I can try to make it larger. So not so large, let's say so. I'll make it like this. And you can see here, I can vary for those things. This is number of tosses. And here is the probability that you toss, that you have heads or tails. So you can see that it goes. But here, nothing is so interesting. But you can go forward and see that if we just select 20, so and it could be 20 or etc. So we can just try to have it. But this thing was studied by the scientists, and here one important thing we can speak about the person who was called Abraham de Moivre. and he lived in the 18th century. He was basically a statistician and consultant, and he was often asked to make long calculations concerning some kind of games of chance. And then he noted that when the number of events increased, the shape of the binomial distribution approached a very smooth curve, and he saw that he would be able to solve these long calculations problems by integrating the areas under the curve probably, etc. But if he could find a mathematical expression for this curve, so he didn't know still what is the expression. And then this is exactly what he did, yes. And then the curve he discovered is now called the normal curve. So you know that the normal curve, and you know that's 1 of 2 pi square root, etc. So this is like the normal curve. So Moaver was defined there. Moaver, by the way, introduced a new theorem, which we will study later. It will be like with the complex numbers, and you can see them here. But before that, the late 1870s, the normal term was used also by different other mathematicians independently. And it also doesn't mean that if you use normal, it's not mean that all other distributions are not normal or abnormal. Yeah, so please pay attention to that. Let's go further. And here you can see an interesting thing when you try to draw the distributions of probabilities with different kind of things. What is here? For example, you see n is 25 all the time. So it means that you have 25 trials. And if you have, for example, if you just toss a coin and the probability that you have heads is 0.15 and the probability that you have tails is 0.85, so it's a biased coin, then you can see that the graph looks like that. And here is NP and NQ. Remember, NP was a kind of mathematical expectation for binomial distribution, yeah? And NQ is just n times the probability of that you have like complementary probability. And you can see here, the thing is that these numbers do tell us a lot. And here you can see NP is 23 and NQ is 1.25. Here NP is 1875 and Q is 6.25. And here it is the following, here the following. And what you can see here, these two are very good approximations of binomial distributions to normal distributions. So here you can use like a normal distribution curve. You can see here like very good shape. And here as well. But in those cases, we can see that there is something lacking here, and this is not a good shape. So these are not so good approximations. And if we do make detailed investigation of this, we can create the following. If NP and NQ are both greater than 5, then we can use normal shape instead of binomial distribution. This is important. And you can see here, these are very good things, because here you have like those. And then it means that if you have, for example, a distribution which is binomial, look, what does it mean here? It is number of trials and the probability of a good trial. Yeah. So let me try to see that if you have 40 multiplied by 0.9, oh, sorry, 0.9. This is how much is this? 9 times 4, and it will be 3 times 6. Yes, 3 times 6, and it is less than 5. And oh no, it is like 40 times 0.5. It will be okay. It will be 36. But if you have 0.1 with that, it will be less than 5, and it's not going to be a good approximation of a normal distribution. So we have to make it out. And here you can see if you have let's say so, distribution which is 250 and 0, 2, then here it can be well approximated by a normal distribution because NP will be 50 and NQ will be even 200 because 250 multiplied by 0.8. And then they both are greater than 5, then you can use approximation. So this one is you need to understand. So this is the key point. Please remember this for solving the problems. This is very important. And then afterwards, if we approximate a discrete distribution by a continuous distribution, you have to remember that if we have a discrete value, like x equals 13, it cannot be calculated like this in the continuous distribution because the probability, if you have continuous distribution of one single value, is just 0. So you need to introduce the class, and then the class will be the following. So if you have normal distribution, so you just take the class like from this number minus 0.5 and this number plus 0.5. So this will be the class. And here you can see this is like less than or x is larger than or equal to 12, 0.5, but x is less than 13.5. And for this reason, like x equals 13, it can be replaced by either this or by that in our probability calculations. This is a very important thing. And so it means that if you do this replacement, you are making a continuity correction. And in the exercises, you often have make continuity correction or keep continuity correction. So use the continuity correction. So please pay attention to that. If you don't understand this, ask me questions afterwards. But this is important. And deciding whether to use this or this depends on whether or not this is included or not. So we have to understand whether it's included or not. We will see it in examples, you will understand it. So if we have example, look, we wish to find the probability that x is less than 13, where x as 13 is not included. You see, not included because you have less. Then we calculate, we take this one for calculation. If you want to find less or equal than 13, then of course x is included this, and then we're using this, the upper bound of the class. And here we can see the example. Yes, look what we have. We are given a binomial distribution, and we have to find a suitable approximation and continuity correction, and then we have to find the following and the following. So here we have to find that P is less. So remember, so here we have 100 trials, and the probability, positive probability of one trial is 0.4. So in order to find the probability that the trials are less than 43, you need to find all the probabilities for 0, less than 0, less than 1, of 1, 2, 3, 4, 5, and that. So this is a big job. And it's not worth doing that, but you can use approximation. You see how good is this if you use approximation. And in this case, if you use approximation, you need to create the following. So you need to use you need to apply the normal distribution. And how you can use this one? So you can approximate it by that, but you have to find the normal distribution. You need to find here. Remember what were there? It was mathematical expectation and variance. And then here you have number of trials and the probability. So you need to find that. Let's see how it is done. First of all, we need to check if we can do this, because remember, if we can do it, we need to find NP and NQ. NP, you know, it's mathematical expectation, so it's like expectation, and then if you use this one, then you can see it's 40, but then Q is 60, so then it means like they both are, Q is 0.6 and then NQ is 60. So both of them are good, larger than 5, so you can use this approximation. This is important. And then if you want to find the continuous distribution, we need to see, so first of all, we need to find the normal one. And normal, you can see here, NPQ is sigma squared. It is from the binomial distribution that we know NPQ is the variance and NP is the mathematical expectation. So you both find them by using the data that you are given, because you are given N and P, and so you can find Q, and then you can find NP and NPQ. And then this is the normal distribution. And then if you want to find the probability of 43 exactly, yes, then you need to see that 43 is located here, but in between you have to take those class values. And and then afterwards, if you take these things here, that you can say that this value is that in between those little values, and then it means that this is the class, and you can find the single probability. But we need to find the probability of that part, and look what we have here. If possible, continuity corrections for a discrete value of 43 are below. So if you have less than 43, so we would like to use this lower boundary value. If we have less or equal than 43, then we used to have upper boundary value. If we have larger than 43, then we used to have upper boundary value, and if we have larger or equal, then we used to have lower. I hope you understand, because this one is included or not. And if we had to find, in this case, we had to find firstly that probability that you have less than 43 positive outcomes. So then we have to see that this one is PZ than that, because you remember we have to standardize. And if you want to standardize, we know that we have to take the lower bound, because for this, yeah, and then that's why we have to calculate Z. And Z we calculate with this amount. So please be careful and leave 4 digits after comma, because it should be more precise. And then if you want to find this, you know that you can use this part, but here, if by using the table, you don't have a lot of them, so you have to choose only 3 of this. And if you have them, you know like how to use the tables. You have here our table 0.5, and you can see this is 0.5 and 1. I think this was the 695. Let us have a look. Yes, 695. So this is exactly like that. So pay attention to this. And here, if you want to find this probability, you already have found with a certain precision. If you want to have more, like this part, but I think you don't. No, you can have more. Like here, you have 3. No, you don't have, because you have only. Yeah, here you can try to, but it's enough if you have the following precision. So this is the answer. And here, if you want to have larger than 43, remember that if you want to have it larger than 43, then it is the probability that you have. Here you also have this standardization. Again, 43 is included there, so you have this number for standardization, and you are using only 3 digits here. And yeah, because in the picture you can have only 3 digits. You can see this 0.5, 1, and 3, so you don't have more. And here you have 0.714, and you can use only 714. So here you have 0.7, 1, and 4. So here what you can do. And afterwards, you can find that this is approximately to the phi you have found, but you need to find Z1 minus, because it is large. I know we already spoke about standardization and about calculation of all of these things. Yeah, I hope you understand why we have this as the following. And if not, then ask me questions. I will try to explain and record some video again. And then you have this one. So according to the table, we can say 0.1714, 0.71 and 4. So you can see it is 7.1. And if you have 4, you need to add 13 to that. So it will be 0.7624. And that's why here, if you divide it, 0.24, so here you will have it like that. Then this is approximate solution. So this is how you find it. And you can see that here it is really important to approximate, because if we don't approximate, the task cannot be solved easily, because we have a binomial distribution of 100 trials. And if you want to find that less than 43 trials are positive, like successful, then you need to calculate the probability for one single, for each single trials from there, and it will be quite a big calculation. This is important, yeah. So, and now let's have another example that you have here. Here, by the way, there is a tip which you can also use. The tip is that x less than, you know this, yes. Let's try to read it here and remember. But another example is boxes are packed with 8,000 randomly selected items. It's known that 0.2% of the items are yellow, and find, using a suitable approximation, the probability that a box contains fewer than 80 yellow items, and exactly 2 of 3 randomly selected boxes contain fewer than 20 yellow items. So this is interesting. And here you can say this is like that. The first way, you have the binomial distribution, of course, but you have 8,000 items, and the probability that you have yellow item is 0.2%. So that's why you have 0.002, because 0.2%, it is like you need to divide 0.2 by 100. Then here you can try to have, if you try to check if you can use the approximation of the binomial distribution. And here you need to remember, this is the amount and this is the probability P. So you need to find firstly the probability Q, and Q is 0.998. And then you need to take 8,000 and multiply it by this. So what you will get? You will get 16. And then you will have to get 8,000 and multiply by the Q. The Q is here. I hope you understand what Q is. So Q is 0.998, because it is 1 minus P, and this is P. And that's why you have this big number. And they are both larger or greater than 5. So then we can approximate the binomial distribution by a normal distribution. And if we approximate it, so we use mathematical expectation, you see here, and you use the variance. So what we need to do with the normal distribution, instead of those numbers, we need just to find expectation and variance. And here we obtain. So now if we have obtained the normal distribution, we can approximately find the probability that a box contains fewer than 20 yellow items. It means that you need to find the probability that x is less than 20, fewer than 20. So less than 20, it is a strict less than 20, but then you need to standardize. If you want to standardize, we know that x is this, and you know basically 16 is this, but here you have 20, and you know that if you want to standardize, you need to find 20 is the exact number, but you need to find the class. And the class is here 19.5, and here it is 20.5. And if you look for this amount less than 20, so 20 is not included, so that's why you have to take the lower bound. And if you take the lower bound, this is like what you have here. This is your x value. Yes, so this is the x value here. This is the lower bound. That's why you have 19.5. Here, if you standardize, you need to subtract 16. You always subtract the mathematical expectation, and you divide by the standard deviation, which is the square root of the variance. And here you have this one. So everything should be clear here. And then you can use just a good computation. So when you make computation, make it as more precise as possible. And you can see that here, if you leave only 3 significant digits, you will have 876. And now you can look into the table. If you look into the table for 876, you will have to find, this is like that, 876, so 0.87. You see, this is like this, and 6. 0.86, you have to add 16. I think something will be very close to that, and you will find that. You can double check. And please remember, if you use this table, you can also see the critical values. If you have some of these critical values, you have to find this thing. So this is done. And the next thing you have to do was exactly 2 of 3 randomly selected boxes contain fewer than 20 yellow items. So if you solve this, you know the probability that you have 20 yellow items, but now you need to compute that these boxes 2 of 3 compute them. So here you need to remember, this is the probability that you contain yellow item. 20 of the boxes contain yellow items. Yes, so this randomly selected 20 boxes, and here you have, and then just if you have 20 boxes, and here you have, these are the contained, that they contain yellow. This is that they don't contain yellow, and then you have 3 over 2, the combination, because you can, if you have selected 3 boxes, then this, each of them box can have either it is yellow or not. So that's why if it is yellow, it is this. If it is not yellow, then this. Now, of course, if you select 3 boxes, you have 2 yellow and 1 not yellow. And then you have the combinations. How many different combinations are there? There are 3. And that's why you just do this like this. I hope you understand this. And here you can see that this 0.375. And now you can see how you can do that. But it is possible to compute as well if you have the binomial distribution like this, because when you have this fewer than 20 yellow boxes items, the y yellow will be binomial distribution of 3 successful trials, and here you will have 0.8094. But it is a little bit harder to calculate. It's better to calculate approximation. But here at least you can do it, and you can try to compare that the numbers will be similar. So if we go further, we have here one more example. You can see a fair coin is tossed 888 times, and we have to find, by using a suitable approximation, a probability that the coin lands heads up at most. So what does it mean at most? It could be less or equal to that. Then, of course, if we have the binomial distribution, when we have this, we need to approximate it. But if we want to approximate it, we need again to check if NP and NQ is larger than 5. But N is this amount and P is this amount. So Q will be also 0.5. So that's why we multiply this by P and we get 444. And we have multiply the amount of trials by Q and we get them also 444, and they both are greater than 5, so we can use the approximation, and then we can find the variance by making NPQ. As you know from the binomial distribution, the variance is NPQ, and it is 222. And then we can put it into the normal distribution, and this normal distribution will approximate this kind of distribution. Please remember. And then if we have the normal distribution, we can standardize it, and then we can easily find when probability is less than 450 or larger than 450, etc. So here, less or equal to 450. So here you just find this probability. And here again, a question about this number, where we take it from. Please remember that you want to approximate a discrete distribution by continuous. So then that's why you need to make a continuity correction. And if you make a continuity correction, again, you need to take 450 is in the class like this. So here 449.5 and 450.5. And why you are using this exactly upper bound because you want to include 450, and if you want to include 450, you need to use the upper bound. Yeah? So here there is no discrete value, but this one will be included. That's why you're using that. Of course, here it's a standardization, similar procedure. So remember standardization, if you want to find z, it is equal to x minus mu is the expectation divided by sigma, yeah, so by standard deviation. And this is the formula for the standardization, so that's why I hope you understand this. And then if you calculate it using the calculator, it will be this number. And then now you can just look up into the table, you will find this value, and this is this, and this is your answer. So at most, you can approximate it up to 3 significant figures, and the answer is the following. So this is how we look like. And here, the exercises I will give you to solve now, you can solve them. And today, if you solve exercises, if you find them, that's good. If not, then give me the feedback and I'll solve them for tomorrow. You'll have a look before the test. So here, visiting the binomial distribution resource in GeoGebra, you can do that, yes? If you go into and you can see that here you can select all these pictures. I can show you these things, how they appear. So maybe it is also interesting for you. And then we finish for today. So here, if you just move this distribution here, you can see, yeah, let's do it like that. This is the picture. And you can see here, we can approximately change the amount of trials. You can change the probabilities, and this is how it goes. So this is how it goes. Okay, thanks a lot. Hope you understand. If not, in the comment here, just write your questions. I'll answer them.